A hint is given here for the proof of proposition 2.1, which I just explained in the last video, and you can take this as an exercise and try to write down the proof, and maybe as a review exercise for the first exam. And the next, proposition 2.3. A diameter perpendicular to a chord bisects the chord and bisects each of the arcs determined by the chord. Look at this picture here. We have a chord AB. So this chord divides the circle into two arcs, one major arc and another minor arc. And if we draw a perpendicular diameter, so this chord CD is through the center O, so that's why this is a diameter. And if we draw this diameter, there are many, we know there are infinitely many diameters, so we can draw any line segment through center O, but we draw the special one, which is perpendicular to the chord AB. So this is a right angle here, AEB, and we want to prove that this diameter must be a bisector of AB, which means it cuts AB into two equal half line segments, AE and EB, and also it bisects the minor arc. The arc ADB is cut into two equal half arcs, AD and DB, and also the major arc ACB, the arc AC and arc BC are congruent. So that's what we want to prove in this proposition. Give you a hint here. We want to prove that we join AO and BO, so we get a triangle AOB. Now we can prove the two triangles OAE and OBE are congruent. This can be proved easily by SAS, because this is a isosceles triangle, because AO is the radius and BO is also radius of the circle, and by the definition of a circle, they should have the same radius. The radius is always the same, fixed, so AO and BO should be congruent to each other, and also they share a common side OE, and the angle between AO and OE is equal to 90 degrees minus OAE. And the angle between OB and OE, this angle is also equal to 90 degrees minus OBE. And we know this is isosceles triangle, so OAE and OBE are congruent. That means the complementary angles AOE and BOE are congruent. So we can prove this by SAS, that these the triangles are congruent. So once we prove these two triangles are congruent, of course AE and BE, the corresponding sides, they should be congruent, and so that means CD is a bisector of AB. And also by the proposition 2.1 we proved before, if we have to prove AD and arc AD and arc BD are congruent. If we go to the last slide, when we want to prove two arcs are congruent, there are two propositions. We can either prove their central angles are congruent, or we can prove their corresponding chords. The chords are congruent. So either way, and if in this case, it's very easy to prove the central angles. For example, what's the central angle of a arc AD? It's AOD, and we just proved AOD and BOD are congruent. So of course these two angles are congruent, and that means CD bisects the minor arc AB. Well, similarly we can prove the CD also bisects the major arc ACB, because the major arc, the measure is 360 minus the minor, or actually we can just use 180, because half of the circle, semicircle, is 180 degrees, and the angle angle AOD plus angle COA is 180. So of course angle COA is 180 minus BOA. And similarly, on the right side, angle COB is 180 minus angle BOD, because AOD and BOD are congruent, of course. The rest of it should be congruent. So I give you a hint here, and basically I go over the proof steps here, and what you need to do is to write down the formal proof as a practice for the midterm exam. And first to try to draw a different picture and connect AO and BO and follow the steps. And the 2.4, if two circles intersect, so we draw two circles, one big, one small. It doesn't matter, actually they can have the same size, same radii. The line through their centers, so A here is the center of the small one, B is the center of the bigger one. We join these two centers, we get a line segment AB. And then these two circles intersect at C and D, and we can connect these two intersection points, we get CD. So AB is a line segment through two centers, and CD is the line segment through the two intersection points. And what's the relationship between them? From the picture we can see it looks like they are perpendicular to each other. And also notice AE apparently is not congruent to EB, but from the picture it looks like CE is congruent to ED. So we may conjecture that actually it is correct that AB is a perpendicular bisector of CD. This can be proved very easily if we use the corollary we had in section in chapter first section 1.3, the corollary 1.3, the section 1.1 on page 21. If we look at point B, this is the center of the big circle. So BC, and if we connect B and D, BC and BD, they're both the radii of the big circle. So BC and BD are congruent. That means B is equidistant from C and D. Similarly, if we look at the point A is the center of the smaller circle, and AC is the radius of the small circle, and AD is also the radius, because C and D are both on the circle. So up from the center to a point on the circle, that's the radius. So AC is the radius, AD is the radius, so AC is congruent to AD. That means A is also equidistant from these 2 points, C and D. So we have, since both A and B are equidistant from the line segment CD by corollary 1.3, line segment AB is the perpendicular bisector of CD. So this has been proved before, so we can just use corollary 1.3 directly here. Next, we look at definition, tangent to a curve. So this is a curve, the black curve here, and there's a point on the black curve. We draw a red line. This line is called the tangent line of the curve. So what's a tangent line to a curve? A tangent at the point P to a curve is a line containing the point P and having the same direction of the curve at P. If Q is another point on the curve, so if I pick another point right here or here, or maybe here, and I connect P and Q, this is called a secant, and similar to the secant of a circle. If I move this point Q, so this red dot here is P, fixed point, and this one here, if I can move this point on this curve, if I move it, then the red line segment will also move, and then we'll get, as Q gets closer and closer to P from either side, both sides, and then PQ approaches the tangent line to the curve at P. This is if you had taken calculus 1 in calculus A, we have explained this, how to define exactly how we define the the tangent line, and how to find the limit at this point. The derivative at this point. I will post a link to flash to this I just explained here. So basically, intuitively, it's a line which only touches the curve. Where it can touch the curve, intersect the curve at many points, but right here in this small area, there's exactly one intersection point. So now, definition of a tangent to a circle. So this is we can consider the circle as a special curve. So that's how we draw a tangent line. And the definition: a tangent to a circle O at a point P on the circle. Well, in this case, I have a point B here. On the circle is the line through B perpendicular to OB. So this point B is on the circle, and the AC, this line AC, is the tangent line to the circle at point B, which is also perpendicular to OB. O is the center. If we join O and B, it should be perpendicular to the tangent line. So that's the definition. So we need to remember the definition of the tangent to a circle. Always remember, if we have a tangent to a circle, the intersection point P if we connected this point P with the center, we get a line segment. They must be perpendicular to each other. So we get a 90 degrees angle here. So that's very useful in the proofs. Okay, theorem 2.1. The measure of an angle formed by a tangent, we have in this picture, ST is the tangent, and a chord is PQ. Or we can consider this, if we consider this whole line, it's a secant. So we have an angle. If we forget about the circle and everything there, this is the tangent, this is a chord, and the angle formed by then in the picture, we use alpha to denote the measure. So this angle here equals half of the measure of the intercept arc. So the intercept arc between these two lines is this minor arc is PQ, and we want to prove this angle is half of the measure of the arc. And recall the definition of our arc, the measure of arc. It means also we remember the measure of arc is also the measure of this central angle here. So basically in the picture, we want to prove alpha is half of beta, because the measure of PQ is defined as the measure of the central angle POQ. And well, we also consider there's a bigger angle SPQ instead of this small angle alpha here. So similarly, can we prove SPQ, this big angle, and the arc, the major arc from P to Q, this major arc, can we prove this angle is also half of this major arc? So we have two things we want to prove. The first, we want to prove this small angle is half of the small arc, the minor arc we call. And also we prove this big angle SPQ. SPQ is also half of the measure of the major arc PQ. So we're going to explain the proof in next video.